In this talk, we will study the problem of maximizing a submodular function in a streaming setting. Submodular functions are an important class of discrete functions with many applications, including image summarization, video summarization and fMRI parcellation. Intuitively, a submodular function is a function that obeys the diminishing returns property. In words, the marginal contribution of adding an element to a set diminishes as the set becomes larger and larger. In many practical scenarios, the collection of elements to be summarized is generated at a very fast pace often. And it is important to maintain a real-time summary of these generated frames. For example, a surveillance camera generates a continuous stream of frames, and it is desirable to quickly get a short summary of the frames at every given time point. The naive way to handle this task is to store the entire set of frames, and then use an offline algorithm to generate a summary out of the stored frames. Unfortunately, this approach is not practical. Because it requires the system to store the whole dataset, and the generation of the summary from such a large amount of data can be very slow or even infeasible. These issues motivate us to use streaming submodular maximization algorithms. In this paper, we introduce a new randomized streaming algorithm for maximizing a submodular function subject to a p-matchoid constraint. A set system N(I) is a p-matchoid, for some positive integer p, if there exist m-matroids such that every element of n appears in the ground set of at most p out of these matroids. It is important to note that p-matchoid is a very general constraint, which includes, in particular, cardinality and matroid constraints. Our algorithm, called sample streaming, samples every element of the stream with an appropriate probability q, and then feeds the elements that have not been dismissed into a deterministic algorithm for maximizing a monotone submodular function. The random dismissal of elements gives the algorithm two advantages. First, it makes it faster because there is no need to process the dismissed elements. Second, it transforms an algorithm for monotone submodular functions into an algorithm for non-monotone submodular functions. Dismissing elements at random also have an obvious drawback. The dismissed elements are likely to include a significant fraction of the value of the optimal solution. The novelty of the analysis of our algorithm is its ability to show that the loss of value due to the random dismissal of elements does not affect the approximation ratio. In this table, we compare sample streaming with the state-of-the-art algorithms in various settings. We observe that our algorithm provides the best of three worlds. First, the tightest approximation guarantees. Second, it has the minimum memory requirement. And finally, it makes the fewest queries per element.